Now we're going to describe some common sampling schemes that will allow us to quantify the chance error that involves in any sampling process. So a big takeaway here is a huge sample size is not going to fix a bad sampling method. My analogy here is tasting soup. If it's well stirred, a spoonful is all you need. But if it's not well stirred, then you're going to need much more than a spoonful to be able to get a good representative sample of the population. So this is a phenomenon we're going to have you explore more in depth in one of your assignments where you'll perform an analysis of the 2016 US presidential elections. The key takeaway here is the easiest way to get a representative sample is by using randomness. Okay, what do I mean by randomness? A random, aka we're going to call it a probability sample, is specifically a sample that has these characteristics. Before the sample is drawn, you have to know the selection probability of every group of people in the population. Or if it's not people that you're sampling, of every group of the elements in the population. Note that not all individuals or groups have to have an equal chance of being selected. Why do we have this framework for using a probability sample? Well, as long as you can define the selection probability of every group of people, then you can quantify the random chance errors that will occur in your sample. Also, this is going to help give a more representative sample of the population, which will help reduce bias. Now, I'm going to point out this is only the case when the distribution we're sampling from, your sampling frame, is accurate. And so this is why you want that sampling frame to, as much as possible, be equal to your actual target population. Random samples using bad or inaccurate sampling frames can produce biased estimates of your population. Probability samples allow us to estimate the bias and the chance error, which is going to help us quantify the uncertainty in our estimates. And we're going to look at this much more when we visit confidence intervals in a future lesson. Okay, so for a probability sample, you have to be able to provide the chance that any specified set will be in the sample. However, it's not the case that all elements in the population have to have the same chance of being selected. The upside is because you know all the probabilities, then you're able to actually measure the errors. All right, so this is the ideal math model world. The real world is usually much more complicated. So how do I come up with a probability sample, for example, for election polling? It's nearly impossible for me to be able to quantify the chance that any specified set of individuals will be in the sample. Or bacteria. I don't know the probability that a given bacterium will get into a microbiome sample. So in these cases, where my sampling measurement process is messy because it's in the real world, we try to do our best to actually model the situation. All right, so what do I mean by this? Again, I'm just summarizing. If we have a probability sample, we can quantify error and bias. Given the population distribution, we can compute the probability of us getting a particular sample. This is almost never really the case in reality, but it's a good start. And so there are several models that are special cases that we can use. This example of randomly sampling with replacement from a categorical population will produce results that can be well modeled by the multinomial distribution. So let's look at this case. Let's look at this random sample with replacement. This is a type of sample that is drawn, we're going to say uniformly at random. That means that every element in the population has an equal probability of being selected in a given draw. That's the uniform part. The with replacement means once you select that person, you record their whatever thing you're surveying them about. So if it's who they're going to vote for or their height or whatever it is, you record that, then you put them back into the sampling frame that you're sampling from, and then you resample. So some individuals in the population might get picked more than once. in this sampling scheme. This sampling scheme is very well modeled by a multinomial distribution in the cases where you are trying to have them answer some type of categorical question like yes or no, are you going to vote for this candidate? Or is your height in this given interval? Now, in reality, we usually don't do samples with replacement. And so in reality, we usually do what's called a simple random sample. And that again is uniformly at random, but this time without replacement. So every individual has the same chance of being selected. Every pair has the same chance as every other pair. Every triple has the same chance as every other triple, and so on. This scheme is not exactly the same as a multinomial distribution because I'm not sampling with replacement. So as soon as I sample somebody, it changes the underlying distribution. But we're going to see that we can actually make some assumptions that this simple random sample scheme can be well approximated by a multinomial model in the cases when your sample is much smaller than your overall population. And we'll see that in a minute. So a raffle could use either sampling scheme depending on whether or not winners are eligible for multiple prizes. All right, so these are the two most common ones that we'll use in this class, but I just want to point out there are some other commonly used probability sampling schemes. One of them is called a systematic sample. And in this one, you order your sample frame based on some type of order that you choose. Maybe it's alphabetical order, maybe it's numerical order. And then you choose an integer and you sample every kth unit in the sample frame. That is, again, a type of sampling where we can quantify the chance error that will result. And a fourth common random sampling scheme is called a stratified random sample. So if you have a heterogeneous population that can be broken up into homogeneous groups, for example, all CU students, I could break them up into, say, their year, freshman, sophomore, junior, senior, or fifth year plus. Then I could randomly sample from each group proportionate to their prevalence in the population. And that's called a stratified random sample. All right, but for the purposes of this class, because it's easiest to model a random sample with replacement and or a simple random sample, that's what we'll be using for our examples. I want to contrast this with a convenience sample. So a convenience sample is when you sample whoever you can get a hold of. For example, whoever visits your website or whoever walks by your polling table. Even though that may feel like you're sampling randomly from that group, right? Maybe I randomly sample people who visit my website. I don't actually have what we're calling a random, aka probability sample. Because if you can't figure out ahead of time what's the population, so who's going to visit your website and what's the probability they're going to visit your website, and what's the probability you select them for each group in the population, then you don't have a random sample. And again, the downside of this, the convenience sample has all kinds of downsides in the sense that you can introduce selection bias, but in particular, you're not going to be able to quantify your chance errors if you use this type of sampling. So we will strongly suggest to not use this technique and to be very wary if you're given data that has been collected using this technique.